Hi friends, today I'm going to talk about Jordan normal blocks and the Jordan chain basis. So from the last video, we know that we can express A as xj x inverse, where instead of having a diagonal matrix, because all matrices might not be diagonalizable, we have this J matrix. And what this is saying is that, okay, A might be defective, meaning that we don't have a full set of eigenvectors for this A, but we can almost do as well by introducing the generalized eigenvectors. So we said that A minus lambda I times a kind of a real eigenvector, so to say, or like our original eigenvector, that's just going to be the zero vector. But we said that we allow, if we say that our generalized eigenvector here, v2, we can allow it to be v1 instead of 0, which means that if I substitute v1 here into this equation, we know that we can just plop all of this into the position of v1 right here, and that's going to give us a minus lambda I, and then a minus lambda I again, v2, is equal to 0. So then we get the equation a minus lambda I squared is equal to 0. So we say that we kind of need to go this extra step to get our 0. And now I want to show kind of why this works. Why can we even get this form in the first place? And to do so, I'm first just going to rewrite this in another format. And I'm going to do it by just multiplying on x on the right on both sides. And this is just so we can reason about a, x, and j without having to worry about the inverse. But we know that if j is equal to this kind of lambda here, we know that x will be composed of a full set of eigenvectors. We know that we will have n eigenvectors. And then, because x will be kind of full rank, that it will have n columns and linearly independent columns, we know that x must be invertible. So x must be invertible. And then we know we can kind of go the other way. Then we know that we can multiply by x inverse and get back into this form that we can then use to take matrix powers and everything else. But if J is not a diagonal matrix, in this video I want to show that we still can end up with an invertible matrix. We still want to find this X composed of now eigenvectors and generalized eigenvectors, such that we still come up with, so we have n eigenvectors slash generalized eigenvectors, that we still end up with an X that is invertible. And first of all, I just want to kind of recognize why this format even makes sense. So for example, let's say that we have a Jordan normal form and we have our X. And let's just say my X is composed of 3 columns. So I'm going to say that we columns v1, v2, and v3. And here I'm going to say that all of these ones will have the same eigenvalue. So we're all going to have the same eigenvalue lambda, but I'm going to say that only v1 and v3 are the actual eigenvectors, and that v2 will be our kind of generalized eigenvector. Okay, so now if I take ax is equal to xj, I can express this as a, and then x is just going to be my v1, v2, v3. And then I want to have my x again on the right, so v1, v2, v3. And then I have my J matrix. And now I want to show to you why this matrix will look something like this. Lambdas across the board, but we're going to have a 1 here. I'm going to show you why this works. So I just said that v1 and v3 are our kind of real eigenvectors, our original eigenvectors that we talked about. And if I just do this multiplication on the left, we know that this is going to be a matrix where we have AV1, AV2, AV3 is equal to, and if I now know that V1 and V3 are eigenvectors, that means that when I take AV1, this must be lambda V1. And this must also be lambda, but in this case, V3. So I want these two vectors to come out as lambda V1 and lambda V3. And we can see, if I just do my lambda and a column right here and multiply it by this thing right here, we see that we're only going to pick out lambda and the V1. So indeed, our first kind of entry here is going to be lambda V1. And then if I look at the last column, so the last column right here, that's also going to kind of pop up and take the whole thing. And we see we're only going to use the last entry here is going to correspond to this last entry right here. And what that's going to mean is we have the lambda V3. But now, why do we have this 1 right here? So in that case, so if I say that AV2 is a generalized eigenvector, what I wanted to say then is that AV2 is going to equal, and what happens now? If I take 1 and lambda and 0, that's going to kind of go up here. We're going to have 1 times V1 plus lambda V2. So this is going to come out to be V1 plus lambda V2, just like that. So if I write that, V1 plus lambda V2, and then I'm going to do the trick where I kind of throw the lambda V2 to the left side. So this will give me AV2 minus lambda V2 is equal to V1. And then if I factor out the V2, I'm going to get A minus lambda I V2 is equal to V1. And this, as I said before, was exactly our definition of a generalized eigenvector. As you can see, these two are the same. So that means that when we have this 1 above one of our lambdas, that means that we're taking a generalized eigenvector. And when we have the 0 above the lambda, that just means that this is an eigenvector in its own right. And what we kind of say then is we can kind of have these two blocks in this Jordan matrix. We can kind of say, okay, we have one block of lambda here with the 1 above, and then we have this lambda on its own. And why did I put these in the block? Well, because we have this 1 here, it means that it's associated with this other lambda. And because we're associated with each other, that means that we're kind of derived from each other. We kind of stay together a little bit. So that's why I put a box, because they are related. Because V2 directly gives us V1 when multiplied by A minus lambda I. And this is exactly a Jordan chain. What we said here is that V2 and V1 form a chain. We can think of it as our V1 is kind of right here, and then one layer above it or out of it is this V2. And together they kind of form this chain that if I apply A minus lambda I can go from V2 to V1, and then when I apply A minus lambda I again, I'm going to go from V1 to 0. So they form a chain. And then what I can do is I can say, well, okay, so I already know that V1 and V3 are eigenvectors, and then these two kind of come together as a little pair. So often we would note this and say that, okay, the Jordan kind of chain basis, is going to be then composed of V1, V2, and then also of V3. And we're denoting here with these squiggly brackets right here that V1 and V2 are related. And remember, this can kind of go on for quite a while. And this form then lets us reason about and C, the algebraic multiplicity and the geometric multiplicity. So we know that the geometric multiplicity is going to tell us how many eigenvectors are there. How many eigenvectors are there for lambda? And in this case, that was 2. We had 2 eigenvectors for lambda. And that means that this will correspond to the number of blocks. So the number of these Jordan blocks for lambda. So in this case, since we had 2 eigenvectors, we know we will have 2 blocks. Because we know that, okay, we're going to have 1 block for this eigenvector, 1 block for this eigenvector, and for all the things that we're kind of missing, well, we're going to derive those missing eigenvectors from those first eigenvectors. So if you know how many eigenvectors you have, you know how many chains you will have, and then how many blocks you will have. And then we can say, well, okay, if we had 3 eigenvectors, then we know that the matrix would have 3 blocks. We would just have 1 chain, 1 block for each eigenvector. And voila, now we have our diagonal matrix as we had before. So then we can reason about and just have our full set of eigenvectors right here. We would say it's invertible and we would be able to move on. But then as soon as we have one of these, for example, as soon as we are having a defective A, we know that we will have a 1 even in 1 spot, but we maybe even have it in 2 spots. Like what if we only had V1 as our eigenvector, and then we would have to derive V2 from V1, and then derive V3 from V2. Then we would have this form, and then it would no longer be a diagonal one, it would be what we call J. So okay, if we know that X then is composed of V1, V2, and V3, and even all the way up to, let's say, VK, and where some of these ones are eigenvectors and some of these ones are generalized eigenvectors, how can I prove to you that this matrix X is still invertible? And I want to show that X is still invertible. X is still invertible. And to show this, I'm going to rely on what we saw before. So previously we saw that A minus lambda I V2 is equal to V1. But if I'm generalizing this to our kind of kth generalized eigenvector, we're just going to say it's going to be the vector that came before it, right? So if I have A minus lambda I, for example, use my V1, which is the eigenvector, I know this is going to be 0, and then I can take this to any power that I want, and it's going to be 0. So if we have this form, we saw that here we had to apply A minus lambda I twice to get to 0. So again, if I apply A minus lambda I to the k to one of our vectors, I am guaranteed to get the 0 vector. So now to prove that if I have this matrix, which is going to be of eigenvectors, but let's just say the first one is an eigenvector and then all of these other ones are kind of the generalized eigenvector, how do we show that this is an invertible matrix? Well, to show that, I will show that all the vectors are linearly independent, and that means that we will have a full rank matrix, and when it's full rank, we know it's invertible. What we need to show is that if I multiply all of these vectors by some constant, so I'm going to multiply it from VK all the way to V1, and I set all of this to 0, I must show that this implies that CK through C1 is equal to 0. That's how we show that these vectors are indeed linearly independent. And to do so, what we can use is this fact that we're can multiply by this A minus lambda I to decrease the powers of K. So for example, if I used multiply once, so if I do A minus lambda I, and just multiply it by the CK, VK, plus all the way to C1, V1, what is this going to get us? Well, on the right-hand side, if I just multiply anything by the left, it's just going to still stay 0, so that's fine. But then what happens here? Well, if I apply a minus lambda I to vk, what's going to happen? Well, if I do a minus lambda I, and this ck is just a constant, so I can kind of put that to the side. But we just set up here that this whole thing is just going to be vk minus 1. So this is just going to turn out to be ck vk minus 1. And then we can kind of continue. What happens if I apply it to the next in line? That's just going to be ck minus 1 vk minus 2. And all the way until I come to c1 v1, in which we can say that a minus lambda I c1 v1, but v1 was our eigenvector, and this is going to be 0. So essentially, by multiplying once on the left, we have zeroed out the eigenvector at the end. So then we're left with the following statement. We have ck vk minus 1 all the way to the next to last one, which would be the c2, but then it would be v2 minus 1. So then that would be v1. That's the same thing as we will transform the v2 into a v1. And all of this must be 0. And now you're thinking, okay, whew, that was a long thing, but we can continue. We can continue on the left. So I can multiply again by a minus lambda I through all of this. And again, I will get ck, but now vk minus 2 all the way down. And because this is a v1, that's going to go to 0. We're going to be left with c3 v1 is equal to 0. And we can continue and continue and continue until this term is the only one that we are left with, this ck. So I'm going to apply it a whole bunch of times. So a whole bunch of times later, I'm just going to cross out all of these other terms until this ck minus 2 moves to be the v1, but we're retaining this ck all the time. So then we're left with this expression. ck v1 is equal to 0. And now we can confidently say that ck must be 0. Why? Well, we know that v1 is an eigenvector. And we know that because it's an eigenvector, v1 must be non-zero. And because it's non-zero, the only way to make this the 0 vector is to multiply by 0. Okay, so if we know that ck must be 0 from doing all that multiplication, we can kind of stick it back in here. Well, we can kind of remove this term right here. And then we can start over. We can say, instead of having ck all that, we're going to say, okay, ck minus 1, vk minus 1, plus da-da-da-da-da, all the way up to c1 v1 is equal to 0. And again, I'm going to multiply by a minus lambda I through all of this. And again, what this is going to do is it's going to decrease the power. So it's going to be ck minus 1, but decrease the power all the way until at the end here we're going to have c2 v1 because it's going to cancel. It's equal to 0. And again, you can multiply, multiply, multiply until you retain this largest constant and you get the v1. So all of this is going to show that we have ck minus 1 v1 is equal to 0. But then again, v1 is non-zero. v1 is non-zero, which means that ck minus 1 must be 0. And maybe you see where this is going. We can then go back up here. We can remove ck minus 1 from the equation, and we can start again with ck minus 2, k minus 2, and go all the way and then get it to 0. So through this process, we can show that yes, indeed, c1 through ck must all be 0. And that means that v1 through vk are all linearly independent. They are linearly independent. And now it's like cue the fireworks, cue everything. So that means we've shown why it even makes sense to put it in this form where we have ax and xj, where j can contain both zeros and ones depending on if you have eigenvectors or generalized eigenvectors. And we've shown that these generalized eigenvectors put into a matrix X will form an invertible matrix. So then I can kind of play this trick in reverse. I'm going to multiply by the X inverse, which we now know exists on both sides. And we're going to get A is equal to xjx inverse. Whew, that was a lot. But that is why this form even works to begin with. And then again, you might ask, well, why do I even want to know why A is equal to xjx inverse? Well, that's a topic of the next video, but just as a little hint, remember about similar matrices? Remember about like matrix powers? All of those things would come into form, because when we have this nice xx inverse, we know that if we chain them, for example, like this, we know that these things will cancel. So we know that A to the n is going to be xj to the n x inverse. And this will allow us to more effectively take matrix powers. We can take e to the a more efficiently. We can take a to the n more efficiently. And we know that if a can be put in this form, a must be similar to j. A and j are similar. And it turns out that if b is similar to j too, we also can state that a and b are similar. So if we can find these Jordan forms, we can find more properties of these matrices, we can start doing a lot more with these matrices in a lot simpler way. So that was an introduction to Jordan blocks and the Jordan chain basis. So we know that, again, why this is a basis is because we are indeed linearly independent. And because we have n of them, we know that those span the entire vector space of A, so that's why it's a basis, and that's why we also have the inverse. So thank you so much for watching. I hope this made it a little bit clearer, and I'll see you in the next video.